Okay, chapter 7, the quantum mechanical model of the atom. Okay, quantum mechanics, kind of hard thing to think about. So, until the beginning of the 20th century, it was believed that all physical phenomena were deterministic, meaning what it's doing now predicts what it's going to do in the future. And this is what we understand just naturally. If I throw a ball across the room, when it's halfway across, we can predict, without even understanding physics, just from our experience, we can predict where it's going to land. This is how 7-year-olds can play baseball, right? They're not as good at it because they haven't had as much practice, but they know that the ball's going to go in that direction. It's going to keep going in that direction. So that sort of makes sense, and that's called Newtonian physics, after Newton. But in the 20th century, people started looking at small things, the extremely small. And they found out that deterministic Newtonian physics idea does not apply to the extremely small. So for subatomic particles, protons, neutrons, and electrons, the present condition, velocity, position, whatever, does not determine what the future condition is. And that's something that's hard to get your mind around because there's nothing in our lives that we can see in the macroscopic world that behaves that way. And so it's kind of hard. So you shoot an electron down a path and measure where it lands. You shoot a second electron down the same path with exactly the same trajectory, and it will probably not land in the same place. That's not how baseballs work. You know, you get a pitching machine, and it pitches the ball, and the ball comes same place every time, right? Electrons don't do that. And so that's what quantum mechanics is about. So here we're talking about the absolutely small, or quantum world. So an electron, now maybe particle physicists would argue with me about this, but as far as I know, subatomic particles, there's a bunch that we haven't mentioned. There's muons and gluons and stuff. But things like electrons, you can't really separate them into smaller pieces. I mean, these are the smallest building blocks of the universe. And so they are the absolutely small. There's not things smaller. And these things behave very differently than the macroscopic world, which is what we can see with our eyes. So when an object that is absolutely small is not being observed, it can exist in two different conditions at the same time. That's not true of macroscopic objects. When we observe that object, the electron, though, it is forced to be in one state, one condition, or the other. So an unobserved radioactive nucleus. A radioactive nucleus will spontaneously emit particles. And so we could think, well, it's either emitting a particle or it's not emitting a particle, right? It can't be doing both at the same time. Yes, it can. If we are not observing it, it is both emitting a particle and not emitting a particle. Error. Overload does not compute, right? Your brain's going, what? Yeah, well, you're in good company because famous scientists had a problem with this too. And I've got some nice quotes from them. So let's think about the electrons. Electrons are mind-bogglingly small. Think of a speck of dust. Teeny tiny dust, right? It's so light, it floats in the air, goes all over the place. A speck of dust has more electrons in it than the number of people who have ever lived on the earth all combined together in a speck of dust. That's a lot of electrons. A little tiny thing that we can barely see, right? Electron behavior determines much of the behavior of the atom. Whether two atoms are going to react and form a compound or not has a lot to do with the electrons. We cannot directly observe an electron because it's so small that when we observe it, it changes the behavior of the electron. It's a little bit like, one of those annoying kids at school, right, who's always acting up when the teacher isn't looking. But as soon as the teacher looks at him, he changes into something else. Question?
You said it changed the behavior, but what does that mean exactly? What changes?
What changes? Okay, that's a very good question, and I don't think I can really answer that yet. So let's continue on with this, and hopefully that will become clear, and if not, ask me again. So even shining a light on an electron forces it to be in one state or another. It can't be in both states at the same time like it normally is when we're not looking at it. Okay, so I'm going to show you two different videos about Schrodinger's cat. And this was a thought experiment. There was no actual cat. No cats were harmed in the thinking about this, okay? In the thought experiment, the cat possibly dies, but it wasn't a real experiment, okay? And the point of this thought experiment, which I think a lot of people miss, they miss the point of it. The point is not that you can have a cat that's both dead and alive at the same time. The point is that the behavior of the ultimately small is not comprehensible on the macroscopic level. And the behavior of the absolutely small does not translate into the macroscopic world. It's almost like two different universes or something. So the laws that apply to electrons do not apply to, say, baseballs. Okay? So let's watch these videos. I'm going to dim the light so that we can see it a little better. And try to get my sound set up here so that we can hear it. I think this should work. There's no sound. Maybe if I turn the speaker on, that might help.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrodinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrodinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment, and it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So that's a fun YouTube channel where they explain physics with a whiteboard marker. Pause. How to subtract by adding. Yeah, you can subtract by adding. Okay, so let's look at this other one.
The art of rebounding is you have to assume that everything's a miss. Rebounds from my team and a rebound from my body. That's what I'm building with chocolate milk. Nutrients to refuel, protein to rebuild, backed by science.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrodinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Think to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrodinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. Now say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrodinger? This is not the best way to get people behind the idea of funding the sciences. So, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws, so it, just like every other cat in history, is either alive or dead. Schrodinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat is dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I Don't Think That Means What You Think It Means, please let us know about that too.
Okay, any questions?
I mean, I got it.
Okay.
Okay, so the Schrodinger's cat experiment, obviously, everybody's heard of it.
Uh-huh.
But, I mean, I'm confused about, exactly what the idea is supposed to illustrate. Because it seems like the concept of Schrodinger's cat asked the wrong question. Okay, so the question is premised on the fact that there's a 50% chance that in this case the atom will decay, therefore releasing a radioactive particle which triggers the hammer.
Right.
But that's not realistic because particles decay at a predictable pace, at a predictable rate, under predictable circumstances.
But you could get a substance where within the time period you've specified, there is a 50% chance that one of the atoms decays.
I mean, but there's, that substance doesn't exist. Even unstable atoms decay at a predictable rate.
Well, they do decay at a predictable
And a repeating rate.
rate, and yet it's not it's on the level of the individual atoms. It's not like, okay, it's your turn. Now it's your turn. It's not that one atom decays every 5 minutes or something. But in a sample, you have so many atoms that we can predict an average rate of decay. But you could have a substance such as that one. The idea is that if you look at an individual radioactive nucleus, well, actually, if you don't look at it, right? If you don't observe it, it is simultaneously in a state of being decayed and not. And that's hard. That's hard to think about.
Is it like it has the potential to be either?
No, it's both at the same time.
Until you look at it.
Until you look at it. When you look at it, when you observe it, you force it to be one or the other.
Here's the tree fall in the forest.
It's a little bit like that, but it isn't, because what is sound? Sound is a movement through the air, and there is sound, whether someone hears it or not. But let's look at these quotes here. Niels Bohr, who was involved in this, said, "Anyone who is not shocked by quantum mechanics has not understood it." Schrodinger wrote, "I don't like it, and I'm sorry I ever had anything to do with it." Albert Einstein attempted unsuccessfully to disprove quantum mechanics until he finally died. This didn't kill him, but, How long was that? The rest of his life. I don't know how long it was. But the people involved in discovering this did not like it. I don't know that there's anyone on the planet who would claim that they completely understand quantum mechanics. It's bizarre. Okay, and so if you're getting this error message in your brain, that's a good sign, okay? If you think, oh, okay, you're not thinking about it enough. It should be confusing. Yes?
If it can exist and not exist at the same time, and it presents like multiple universes, how would you access both? To understand that it's existing and it's not.
That's the problem. So, yeah. Okay, so we're going to look at an experiment that hopefully will illustrate one aspect of how electrons, it's a double slit experiment, and electrons behave as particles and they behave as waves. But when you observe them, you force them to behave as one or the other. Yes?
How do you force them to behave?
The act of looking at them.
Really?
Yes.
So can we have something observe them while we not?
No, you can't. Anything you do to try to get evidence that it's doing both at the same time will cause it to do one or the other. Right?
So could it maybe be the methods we're using to look at it? That
Is it us?
Is it us? Is it something we're doing? It's hard to get your mind around, right?
It's like trying to catch the mirror looking the other way.
It's like trying to smell the color 9. You can't smell the color 9 because 9 is not a color and you can't smell a color anyway. There's a whole song about it. Okay, let's go on here. So what is quantum mechanics? It's a theory that explains the behavior of electrons, or attempts to explain the behavior of electrons. It helps us to understand and predict the properties of atoms that are related to the behavior of behavior of electrons. And some of these things that it helps us to explain are, why are some elements metals and others are nonmetals? Why are some elements shiny and conduct electricity and conduct heat and you can pull them into wires and others aren't? Why? Quantum mechanics helps us to understand. Why do some elements gain an electron to form an anion and others lose an electron to form a cation? Quantum mechanics helps us to understand that. Why are some elements very reactive, others practically inert? You know, helium, there's no known chemical compounds involving helium. It just doesn't react. And then there are other periodic patterns in the table of elements that quantum mechanics helps us to understand.